Welcome to the presentation of a paper called Taming the Chaos, Exploring Graphical Input Vector Manipulation User Interfaces for GANs in a Musical Context. Generative Adverserial Networks, or GANs, are a widely used tool for generating highly realistic artificial data. The basic idea of GANs is that two networks, namely the generator and the discriminator, are trained in an adversarial manner. During training, the generator learns to transform a random noise vector to new data that resembles a specific training dataset, while the discriminator learns to distinguish between real data and the fake data generated by the generator. Subsequently, a trained generator can be used in applications to generate realistic data from noise vectors. WaveGAN, which was first introduced by Donahue and colleagues, is a modification of the original GAN framework, specifically designed for the generation of audio data. An example use case is generation of drum samples, such as bass drum or snare drum sounds. GANs produce not only imitations of familiar content, but also hybrids that still somehow sound natural and realistic. In the case of WaveGAN, this means that unheard of drum samples can be produced that are hybrids of known instruments. An example is a hybrid of a snare and bass drum, which could be called snare drum. This observation led us asking ourselves, how can we use GANs, such as WaveGAN, as a new type of musical instrument or sound design tool? A typical interaction with a trained GAN is generation of a new random noise vector and then feeding it to the generator, which then produces a new and unpredictable output at runtime. Thus, although GANs can produce deceptively real data, such as percussive sounds, users have little opportunity to shape the generated sounds to match their artistic vision or imagination. In order to enable users such as musicians or sound engineers to fine-tune sounds of WaveGAN, we developed graphical user interfaces that enable interaction with a WaveGAN through manipulation of noise vectors, while hearing the resulting output simultaneously. We developed two graphical user interfaces which we call vector manipulation modules. Both vector manipulation modules visualize a 100-dimensional input vector that can be manipulated at runtime by interacting with individual spheres. The picture on the left side shows a vector manipulation module displaying the vector in 3 dimensions, and the picture on the right side shows a vector manipulation module using a 2D constellation. We integrated both of these vector manipulation modules into a web-based drum sequencer developed by Donahue and colleagues. Feel free to try it out online at hcai.eu/pufferfish. When you use a demonstrator, please make sure that you use either Google Chrome or Mozilla Firefox and a PC with a good graphics card. In the sequencer, you can start the drum loop by pressing the play button. You can also modify the beat while it's playing. If you want to modify a certain sample, for example the red one, you can press the adjust button. Afterwards, you can choose a vector manipulation module design you prefer. The first thing I'll do is enable solo mode and maximize the window. Each of the single spheres you see in this constellation represents a single value of the input vector for the GAN. Its value is determined by its distance to the inner core. Also, each sphere is shaded individually to show its impact on the frequency spectrum. Spheres are also sorted according to their impact they have on the whole spectrum. By moving the size slider, you can sort out spheres that have lower impacts. I will now disable solo mode again so I can hear the new sample in context. I will now demonstrate the second vector manipulation module called slider array. Over here we have a 2D constellation of sliders that can be manipulated to change sounds. The sliders are also sorted according to their relevances. By pressing the reshuffle button, you can search for a completely new random sound. If you like it, you can still fine-tune it with the sliders. Next, I want to modify the sound of the green drum. I switch to the Fibonacci sphere vector manipulation module, enable full screen mode again, and search for a good starting point using the reshuffle function. I continue searching for a sound I like by sorting out lower impact spheres and experimenting with the remaining ones. Some minor changes in the end. And finally, disabling solo mode so I can listen to it in context. To evaluate our approach, we conducted an online user study in which 38 participants interacted with our vector manipulation modules. To participate in the study, participants had to pass a pre-test that tested their basic musical understanding and ability to hear subtle differences in drum samples. With the help of validated questionnaires, we measured user experience, flow, and self-efficacy. In addition, we evaluated logs that recorded user behavior. Furthermore, we asked users for open feedback and their preferred vector manipulation module designs. As a baseline, we used a version of the sequencer that only provided access to random search functions. By evaluating our data, we found that users, if given the option, used fine-tune functions significantly more often than random search functions. Furthermore, we found that users valued the high accessibility and efficiency of the 2D vector manipulation module more than the hedonistic qualities of the 3D vector manipulation module. Evaluating user experience ratings, we observed that vector manipulation modules suffered in terms of perspicuity compared to baseline, while performing better in the novelty dimension. By comparing user-generated samples and target samples, we did not see any difference for accuracy between baseline and our VMM designs. One of the key challenges we identified was the dimensional mismatch between our 3D vector representations and the human interface devices we use that support only 2 spatial degrees of freedom, such as mouse or 2D screen. Thus, we want to assess our approach in mixed reality to provide interaction in 3 spatial dimensions. Furthermore, we observed that participants try to be as efficient as possible due to temporal constraints, which is why we want to conduct laboratory experiments in settings that foster creativity. Finally, since our custom shaders displaying frequency band impacts did receive scarce attention, we want to explore further methods for communicating such affordances. We'd like to thank you very much for your attention.